Welcome back, CHEM152. I hope you all are doing well during this significant time of transition, but we have moved online, so as you can see, doesn't look much different. We've got announcements and outline on the board. I do have the schedule here that I'll update, but these are, as usual, what we do for class. So welcome back. Clearly this is going to be an adjustment. But definitely email or see me during office hours if you've got questions. Homework is available and it's out there. First assignment, chapter 6, it's been posted for a while. That's due on Thursday. And then chapter 7 is due after spring break. I mentioned the office hours earlier. I will send you an invitation for how to get into this. That'll start on Tuesday and Thursday at 9:35 a.m. The quiz and exam will occur after spring break, and you can look on Canvas and you see that some grades have already been posted there. So you can see this is our plan for this video. As usual, need to tie this into the Olympics, our theme for the semester, and then we'll get back to our moles and formulas that we're going to get to. This comes on a day where they're actually talking about postponing the Olympics, but it's really a good time to reevaluate. What were your goals, and now things have changed? What are some new goals that you have? Are they challenging but realistic? Are you going to do something regularly to meet those goals? Can you share those goals with someone that will ask you about that? And then let's say maybe you have a goal to attend every office hour and you miss one. Well, see that as an opportunity. What can you learn from that? Maybe I should get up earlier, or maybe I should do something else. Instead of beating yourself up, look at it as an opportunity to learn. So let's get into where we left off. So you may recall this slide. We're given grams, and we want to go to molecules. So this is one we did in lecture, and the steps are here, but really the roadmap, that's what I'm really emphasizing, is this grams mole particle roadmap. So that's what we're going to pick up on, and we're just going to add to it. So it's good to review here and see where we left off, where are we at. So for grams, moles, this is the molar mass. That's what gets you between those two. So that could be dividing by the molar mass, that could be multiplying by the molar mass, but that's the molar mass. This one is Avogadro's number. So you can see we've got Avogadro's number here that we're multiplying it by. We've got molar mass that we're dividing by. Those were the keys for this grams moles particle roadmap. This was another one that we looked at just before, and that was looking at and emphasizing the molar mass depends on the formula. So if it's bromine, elemental bromine that has 2, you look up on the periodic table, and bromine 79.9, so multiply that by 2 to get the molar mass. Still have Avogadro's number here, and we went from grams to particles, in this case called molecules. So what are we doing now? Well, we're stepping it up, and we're doing that by using ratios. So I know this might seem a little silly, 3 leaves to 1 clover. Well, it's just a helpful reminder that there's ratios of things that can convert. So this is a equality, 3 equals 1. So then your ratio, depends on what you're converting, is 1 over 3 or 3 over 1. So what we're going to do now is do our normal grams moles particles. So that, really wanting that to feel second nature, that you can go to any of these with no problem. And now we're going to make the assumption that that was one substance. So we'll just call that X. We're in grams of X. Well, now what we're going to do is we're going to change it to something else. So moles of X, and we use a ratio right here to go to moles of Y. Well, of course, if we're in moles of Y, Then we can go to particles of Y. We can go to grams of Y. So this is a really critical step here, this ratio. So the 3-to-1 leaves to clover is just an intro. Legs, spider, that's an intro. Legs to chair, 4-to-1, 8-to-1. Now look at what we're talking about, 2-to-1. So if we're talking about molecules of water, there's one molecule of water, but if we actually wanted how many hydrogen atoms, we'd have to double it because there's twice as many. So that's 2 hydrogens for every 1 water. So if we can do that on the molecular scale, then we can do it on the molar scale. So we can scale it up, and the ratio is the same. 3 leaves to 1 clover, 3 dozen leaves, 1 dozen clover. So that's practical things. But what we're talking about is moles. So 2 moles of hydrogen atom for every 1 mole of water molecules. Because we saw at the atomic level, 2 hydrogens for 1 molecule. That's our ratio that we're going to use to go from moles of one thing to moles of something else. So let's take a look here. We've got carbon tetrachloride. Review, that's a covalent or molecular compound. There's no metals. We name the first element, then we use the prefix, name the second element, carbon tetrachloride, which tells us there's 4 moles of chlorine for every 1 mole of this molecule. So let's do a quick check. How I'd recommend you doing these quick checks is you can read it off here, list all the possible atom, formula, unit, mole relationships in barium nitrate, and then you can pause it because I'm going to show the answer pretty quickly. If you look here, we first have to know the name. So that's barium, and if you look, that is alkaline earth metal, so that's a +2 charge. And if you look on the periodic table, you will not find nitrate because that is one of our polyatomic ions that you just have to know. So if you know the charge of barium, you know the charge of nitrate, then you can get to the formula of barium nitrate. Well, now it wants all possible ratios. So you can see that there's 1 barium, and now we have to factor in these numbers. So if there's 1 barium and 1 barium nitrate, there's 2 moles of nitrogen and 1 mole of barium nitrate, and then there's 6 moles of oxygen. That's 2 times 3, that's where that 6 comes from. So we can see that the chemical formula gives us the relationships, but please note, this is not grams. That is really key. What we're talking about is moles when we have chemical formulas. So the roadmap, grams, moles, particles, mole is the critical. So you have to be in moles. All right, so determine the number of moles of oxygen and 2.45 moles of nickel 2 phosphate. Again, you can pause if you want. You got to start with the formula. They tell you that it's nickel 2, and then you have to know that phosphate, PO4 3-. If you've got that, then you can crisscross, and you can also take into account parentheses around the polyatomic, like here. So that's Ni3PO4 2. And if it wants the moles of oxygen, we have to be able to look and say that's 2 times 4 gives me 8 moles of oxygen for every 1 mole of nickel phosphate. And if you're in moles, you can use the ratio and go directly to moles of the other substance. So that's moles of nickel phosphate to moles of oxygen. So now look at this though. The question is grams. What is the mass of carbon in 25 grams of C6H12O6? So go ahead and pause if you want to work on this one. What I'm going to show you is that the real tempting thing here is if you're in grams and the question asks for grams, you want to go directly. So this is grams of X, moles of X, moles of Y, grams of Y. So in this case, we're looking at carbon and C6H12O6 glucose. So a common mistake is to try and go directly grams to grams using this ratio. Remember, the ratio is moles of carbon, moles of glucose. So you have to take grams divided by molar mass, large molar mass here, gets us to moles. Moles of glucose, this conversion gets us to moles of carbon, then we take the molar mass of carbon, that gets you grams of carbon. So roadmap, grams, moles, moles, grams, not grams to grams. We'll come back to that. There's another one. How many grams of sodium chloride contains 1 gram of sodium? Again, you have to eat sodium. You are not going to eat sodium. You're going to eat sodium chloride. So make the conversion. Take a look here. Molar mass. Sodium gets you to moles of sodium. I know this isn't changing the number. It's 1 over 1, but it changes the units from moles of sodium to moles of sodium chloride. So make sure you're writing out your units. Moles of what? Moles sodium chloride. That tells you then the molar mass of sodium chloride is what you need, and you can look that up from the periodic table. So you need to eat 2.54 grams of sodium chloride to get 1 gram of sodium. So this next part then translates into a new word for us, new concept, mass percent. Okay, so whether it's a quiz question, exam question, the terminology mass percent, you need to know right off what that means. So percent means per 100, or that's the whole. Okay, so what you're doing is just taking the mass of whatever you're looking for divided by the mass of the whole times 100. So this can tell you, is it 20% carbon? Is it 30% hydrogen? And so on. So that's mass percent. It's the elements percentage versus the total mass. And you can actually do other things besides the element. You could do what's the percent of nitrate or percent of phosphate. But in most cases, we usually are just looking at the element. Take a look here. We got a chemical formula, a carbon with 2 chlorines and 2 fluorines. So we can get the total molar mass on the bottom. That's something you've done. And now if it says the mass percent of chlorine, the only thing we do is put the chlorine mass on the top. So molar mass of chlorine, 35.45 times 2 divided by the total molar mass times 100. That gets you your mass percent. All right, so calculate the mass percent of nitrogen in ammonium nitrate. You got it. This is another review question of naming. If you don't know the names, you can't do this problem. So ammonium is NH4+. It's a polyatomic ion. It's a cation. Nitrate is a polyatomic ion. It's an anion. And you can see they both have nitrogen in it. So we need to know the correct formula. Since the charges are +1, -1, it's just 1 to 1. We put them together. That's ammonium nitrate. Now you can calculate by calculating there's 2 nitrogens. One there, and then this 80.043 comes from all the other mass. So that's oxygen plus nitrogen, hydrogen plus that nitrogen. And you can see then with the periodic table, you can get lots of sig figs, 35% nitrogen. So remember earlier I said grams to grams. It's really tempting. You want to go grams to grams, but don't do it with the mole ratio. That's an easy mistake. Happens a lot. So what we're talking about is using mass percent as a conversion factor. So you can do this. So when we have 39%, what that means is there's 39 grams of sodium in 100 grams of the compound. That's 39%. So if you take a look then, that's a conversion factor. Grams sodium chloride to grams of sodium to grams of sodium chloride. Grams of sodium chloride to grams of sodium. So now we have a conversion factor from mass to mass. Okay, so let's take a look. If we have the mass percent of chlorine in this compound, how many grams contains 22 grams of chlorine? So again, it's really confusing. We've got to be very specific on our units. That's 22 grams of chlorine. It's asking for grams of the compound. And then it gives you a percent, 58.64% chlorine. So the setup here, it's a one-step problem, but it's really tricky because it's grams of chlorine. Okay, so that's that 58.64. And remember, percent is per 100. So the grams of chlorine cancels with the grams of chlorine, and we're left with the grams of the compound, which is what we want, the answer. So now we go back to our roadmap, and we said, no, you've got to go grams to moles, to grams. That is true when you use the mole ratio. What did we just use here though? We didn't use the mole ratio. Okay, that's the long way. We'll call that the long way. That's what we did before. What we did is went directly grams to grams. And we did that with mass percent. Again, it is a short way, like this problem, if they give you mass percent given, do it. Go directly, grams to grams. However, if you're not given mass percent, then you'd have to set up and solve for mass percent. You might want to just go grams, moles, moles, grams, or this grams to grams. It's up to you. Either way works. All right, so we've talked about formulas, we talked about mole ratios, mass percent. Now we're going to start from mass and get to formulas. So, given elemental mass percent data of a compound, it's possible to find formulas. This is a really common test when you make new compounds. So in graduate school, I made a lot of new compounds and had to figure out what's the formula. Some cases you can find the empirical formula. Some cases you can do even better than that and find the actual molecular formula. So what we're going to talk about is empirical and molecular formulas. So many experiments give you the relative number. That's the empirical. So here, that's what we're going to talk about. Steps, how to get the empirical formula. And then if you've got some more information, you can get to the molecular formula. So that's very specific for that substance. What is the molecular formula? Many things could have the same empirical formula, but only one thing has the molecular formula. So recall, subscripts represent the number of atoms in the compound. And remember, if we're talking about atoms, we can also be talking about moles. So this is key. We need to be in moles. That's our scaling up piece. Sorry about that. That's the subscripts are the moles. Okay, so when you see carbon dioxide, maybe you think 1 atom of carbon, 2 atoms of oxygen, but now really through this chapter, I really want to emphasize you should be thinking 1 mole of carbon, 2 moles of oxygen. That's what those numbers mean, to really emphasize this mole piece, mole, because if you're going to do these kind of problems, you're going to be with lots of grams, but this ratio is all about moles. All right, so here's what we need to do. I've already emphasized it. we got to be in moles. So you got to calculate the moles. Once you calculate the moles, then write those as temporary subscripts. Okay, we know subscripts need to be integers, so this is going to look a little strange, but put these in, these random numbers that you have, as temporary subscripts, then you're going to convert it to whole numbers. Okay, the way we're going to do this, convert to whole numbers, you're going to divide by the lowest to set that one to 1, and then we're going to adjust the others. All right, so you decompose a compound containing nitrogen, oxygen in the laboratory. You got 24.5 grams of nitrogen, 70 grams of oxygen. Calculate the empirical formula. Right away, number one thing, what should we be doing? If we're given grams, what do we have to do? Absolutely, you got to go right away to moles. That is the number one thing. Got to be in moles. So if you take a look, oh, sorry about that. That's the mass of nitrogen. That's the molar mass, getting us to moles. Got to be in moles. Oxygen, go to moles. Now we're in moles, and you can see those are the subscripts. It looks really ridiculous, but this is a really good way to do it. Those are your subscripts. Divide by the lowest, and you get closer to whole numbers. Please don't look at this and think, well, I can just round that up to 3. This is giving you a fraction, it's a half. So what you're doing is taking that and getting rid of the fraction, which is multiplying by 2. And if you multiply this by 2, then you need to multiply that by 2. That's where we end up with N2O5. Here's another one, go for it. Carbon, hydrogen, and oxygen. Same steps, carbon, grams, hydrogen, grams, oxygen, grams, so convert to molar mass. In this case, you've got 3 elements. Same thing, do the subscripts, divide by the lowest, and you end up with CH2O as the empirical formula. So there's several problems you can do on homework are examples of empirical formulas. The last piece to these problems is adding a little bit more information and getting the molecular formula. So the key is you have to have the molar mass of the compound. Okay, so the molar mass of the compound is always a multiple of the empirical formula molar mass. So if you have the empirical formula, you have the empirical formula's molar mass, then you have the molar mass of the compound. You can get the molecular formula, which is what we're going for here in these problems. So take the molar mass of the compound, divide by the molar mass of the empirical formula. That gets you some whole number ratio. So take a look here. We've got 128.16 grams per mole. And we're looking for the molecular formula. Okay, so naphthalene is a compound, this is mothballs, is a compound containing carbon and hydrogen only that is used in mothballs. Its empirical formula, so that's empirical formula C5H4. So right away we should look at this and recognize 128 is not the molecular formula of this. Maybe some of you know this roughly. Offhand, carbon is 12. Hydrogen is 1, so that should be 64. That's the molar mass of the empirical formula. Well, we can look at this right away then. If we see 128, 64, that ratio is 2. Okay, so what do we do with this 2? Well, remember the molecular formula is related by that ratio. So 2 times 5, that's 10, 8. That's what we're doing to get us this molecular formula here. So if you take a look, empirical formula is very general, can apply to multiple compounds. the molar mass of this unique compound, C10H8, is very specific. So we got another quick check, a compound with the following mass percent. So we're starting from the very beginning. You're given mass percent, and you're given the molar mass of the compound. So percents, where do we go from there? So roadmap, percents, go to grams. If we're in grams, where do we go from there? That's right, takes us to moles. Then we go to the subscripts. And we divide by the lowest. So that gets us, we might actually have to multiply. That gets us to our empirical formula. And then remember, we're not done. The molecular divided by the empirical gives us some number to multiply that. So work this out, and you end up with C2H8N2.